host. I'm promoted to host for this. So the next speaker is Dr. Tanvina Patel, and she works as a research engineer for speech systems at Cognit Semantics in Bangalore. And she works on the development of speech recognition, other speech technology applications that enhance enhance human-computer interaction. So, her team's ASR submission ranked second at the Microsoft Low Research Challenge in Indian Languages in Interspeech 2018. And she has 20+ publications and has been a review of interspeech, computer speech and language, and transactions of information, forensics and securities. I suppose, concerning the time, that you read the rest of her bio at in the chat, because I would rather see her speak than to speak about her. So please take the floor.
Yeah, sure. So I hope my screen is visible.
Yes, it is.
Okay, so thank you for that introduction. So I'll give a brief about myself. I'm Tanvina Patel, working at Cognit Semantics, Bangalore. I've done my PhD from DICT Gandhinagar in 2017. For my PhD, I was working in the problem of spoof speech detection. That is, we know that the current TTS and voice conversion systems, they are very natural and intelligible. So the main motive of my thesis was to detect if an incoming speech is human or is it generated by TTS or voice conversion system. This is to prevent spoofing attacks on the speaker verification systems. Since 2017, I'm working with Cognit, and at Cognit, we are developing various speech solutions, and I'll be explaining a few of them here. So, a brief about Cognit. At Cognit, we believe to develop technologies that is easily useful for all. And rather than saying that AI is replacing human, we would like to say that AI is augmenting the human potential. And while doing that, in the process of building AI technology, we have a motive to build safe AI technology and taking care into the concerns of privacy and safety as well. So having more than a decade of years in the AI R&D region, we have developed many solutions, speech, vision, NLP, etc. And along with building products, we have a focus on deep research, publications, participating in challenges, and we are also leaderboards for many challenges. While our association, while our work is going on, we have deep R&D associations with many institutions in India, IIT Bangalore, IIT Madras, IIT Hyderabad, IIT Bangalore, IIT Bangalore, and IIT Trivandrum as well. So these are our growing brand franchisee, ICOG. ICOG is one of the most comprehensive digital learning platform. It redefines learning in organizations. Autobox is generally dealing with the building language-related applications in Indian languages and support other foreign languages. We have many 15+ languages at hand. And combine all of them, we offer our R&D expertise to solve very niche and hard industry problems. So this is a brief introduction about Cognit. In case you would love to hear more, you can talk to me one-on-one, sure. So I'll be discussing about my work today on semi-supervised learning for speech recognition in Indian languages. So I'm sure all of you know the importance of ASR, automatic speech recognition. Is the task of converting an audio. An audio can be in any language, and the task is to convert the audio into text. It is also known as speech to text. And there are many applications of ASR. And one of them is it allows humans to interact with the computer interfaces, be with the digital touch. It preserves language in case the language is endangered. You can build ASR out of it, preserve that. Very important application of ASR is dictation. You can dictate notes, voice-based search, command execution, chatbots we all very know well. Subtitling, we know that many of the movies, series, etc. have subtitles. This can be done by ASR as well. And voice-enabled applications, be it in the medical domain, instead of say doctors or nurses going physically to the software on the screen, moving things around here and there with the mouse, it can be the entire experience can be voice enabled. And one of the major importance application of ASR is speech-to-speech translation. That is, suppose two people do not know their each other's language, we can follow speech-to-speech translation approach, and we can make them communicate in different languages. So this is the system. The ASR generally has a lot of factors that it depends on. ASR is different for read speech and conversational speech. By read speech, what I mean is speech that is very clearly articulated. Say the lecture that is going on now. We say each and every words very carefully. On the other hand, conversation speech is mostly very informal, and we are not at times clearly articulating. Suppose we become very fast while talking with one another. So this both are extremely different, and the performance of ASR depends a lot on having read speech and conversation speech. The second is a clean and noisy speech. The speech that we want to pass through ASR can be clean. In that case, the ASR performance is better. Had it been noisy, the ASR tends to have performance degradation. Speakers can be multiple speakers or a single speaker. It does not matter if it is multiple speaker as long as the speaker are switching. But if they are having overlap, say two speakers are speaking at the same time, it is at that moment when ASR performance drop down. Speaker variability. We know that rate, accent, age, gender, all this are speaker variabilities, and that can drastically affect the performance of the ASR. Then we have ASR that is separate for the channel effects. Say you have something that is recorded on call like this, the meeting recordings. Those are having a different channel altogether, but something, and say it is sampled at some higher frequency, say 16 kilohertz, 48 kilohertz. On the other hand, telephonic speech that we talk to each other via mobile, they are having a different channel effects. So if you train a model on, say, recorded speech, it may not work for telephonic speech, and so on. So there is a lot of performance dependence of ASR on the channel also. Then is the target language. On what are we building the ASR? It has to be a specific language. How hard is the language? Is it having many-to-one mapping of letter and sound? Or is it having one-to-one mapping? Is it having tonality into picture? So tonality, when in a language comes, that means you can say a word in one particular tone, and still the meaning changes if you just change the tone. So you say eh, then you say ah, then the meaning changes. So there are some language like that. Then there's a case of real world issues. When we talk in lecture mode, read mode, we don't hesitate much. We just go with the flow, and there are less of disfluencies. However, if it's conversational, we may have some disfluency. We say, these are all the human disfluencies that are there. We may add new words. When we add new words, say, suppose a normal way of saying is, I'm just searching the content through the web. That is a normal way of saying. But sometimes you just go for a random conversation and you say, I'm Googling. So Googling is not even a word in the dictionary, but you create new words based on maybe multilingual aspects, or just out of nowhere, the new words pop up. So ASR might never have seen those new words, but still you want to recognize them. Another issue is latency. Obviously, depends on the application, whether we want real time or say online ASR, or we want batch processing. So these are the types of ASR that we can develop, and the performance also varies with respect to these factors. Now we know that deep learning technology is it's like huge now, and for at least for limited domain systems, ASR systems can reach almost human level accuracy. Say if it is a read speech, clean, single speaker, normal accent, not so much of accent, we have said that ASR systems can reach human level accuracy. However, this comes at the cost of very huge label data. Normally, ASRs nowadays are built with, say, 50,000-60,000 hours of data, and that's huge data to annotate. So if you want to build a ASR technology or a system for any language, you need to have a huge label corpus. So this is, I'm sure most of you might be knowing this flow. So this is an overview of the ASR. ASRs can be two type. Previously, it was traditionally some few years back, it was hybrid ASR, and now it has moved on to end-to-end ASRs. So what happens in ASR is, first of all, you need a lot of text and data, audio. So as you can see this block here, so you need a lot of data and the annotated data. That is, if this is speech file, you need whatever it's spoken in a text format also. And then you do some sort of signal processing, that is a feature extraction onto it. It can be starting from windowing to MFCC feature extraction, if not MFCC, the PLP feature extraction, length normalization that you want to do, etc., etc. And then those features are fed to an acoustic model. This acoustic model can again be neural networks, HMM based as it was traditionally. And all this acoustic model then combined with language model and lexicon goes for decoding. Now, what is language model? Language model tells us how a text is structured or how it should follow a pattern of grammar, etc. An acoustic model, on the other hand, is a representation of the sounds that we have. Now, if you know in English, suppose we say bat, cat, mat everywhere. So the how does A behave when C is in front of it, B is in front of it, or M is in front of it, is what the acoustic model captures. So it is a representation of the sounds. Each sound has some representation, some approximate representations in the acoustic model. On the other hand, language model, if you see, it's just built out of collecting huge text. We can take a lot of text from the web and build a language model. Basically, language model defines what is the probability of the next word given the previous word. Say, suppose you have to write the tree. So what is the probability that the tree comes and not tree the? So that is what language model does. It gives a structure to your language. Then the third one is a lexicon. Lexicon is just a representation of how words are spoken. Say, if you say about, so you can see you don't say A-B-U-T-E, you say ba, ow sound and T. So that is how the lexicon is actually having, based on the language at hand, it has a description of the word and the corresponding sounds to it. So all this combined is known as all this separately is the hybrid ASR. That is, you have a separate language model, acoustic model, and then you do ASR on it. But now with the advent of end-to-end techniques, what we do is acoustic model, language model, lexicon are all clubbed into a single end-to-end ASR, and we do a joint training of all of them together. So this is an overview of the speech recognition systems. But the problem with most of the systems is they need a lot of data, as I've mentioned, but majority of the language do not have sufficient resources. Resources in the sense they might not have enough digital spoken corpus. Say, suppose you want to build a ASR for English language, you have a lot of open source data. But suppose you want to build a ASR for any low resource language, there's nothing available online. That is one of the categories that fall into low resource language. Second is, even you have audio, suppose we somehow collect audio, we need transcriptions, that is the labeling of the speech corpus. That again requires a lot of manpower to do, and expert manpower who know the language, the text, the orthography in much more detail. So those kind of resources might not be available. That falls under the category of low resource languages. So what is the part I'm going to explain here is, we know that speech data labeling is an expensive task and it is time consuming as well. Suppose you're given a 1 minute audio to annotate, you might take say 5 minutes, 10 minutes, depending upon how accented it is, how normal it is, or see how noisy it is, etc. So speech data labeling itself is a very time consuming and expensive task. So what are we going to do today is we will see how semi-supervised learning can reduce the effort that go into annotation. So we'll have very small data, but still we will build ASR on a larger data set. So this is the overall picture of semi-supervised learning. So we have four major components. That is the seed model. We do decoding, scoring, and retraining. So this is the data at hand. A huge corpus that we have, but we don't have annotations for it. We somehow managed to get a small data annotated. See, this is the data annotated. We then build an ASR out of it, DC seed model. Using this seed model, we take the unlabeled data and decode it. Decode in the sense means we just pass the unlabeled data and get transcripts, that is ASR outputs. Whenever these ASR outputs are populated, they are populated with certain confidence score. Say whether the ASR is 90% confident that the transcript is correct, etc. Once we get that confidence score, we divide the data into high confidence regions and then start adding this data to your labeled seed model. And then what we get is the updated models. So this is overall pipeline of semi-supervised learning. I'm going into much detail over here. We are using here iterative and non-iterative approach. So this is the data I was talking about. We have a DC data, which is a small data out of the bigger pool, and it is annotated. We build a ASR model or say acoustic model out of it and develop a AM seed model. Then we decode the entire unlabeled data set for which we don't have any human transcripts through this model. We get rough transcripts, yes. We also get certain confidence score with, say, for 20,000 unannotated data, you got some 20,000 confidence score ranging into this bins. So this bins will be like this. Say you can categorize this bin or have resolution as much we want. So I have just divided the bins into, say, 10, say point above 0.9 or say bin B1, 0.8 to 0.9 or B2, and so on. So what I do is, so we take this, reorder the data in terms of increasing to decreasing bin. Then we start retraining. We don't correct the transcript. We assume that whatever came in the highest bin is correct. So we take the DSeed model, add our B1 data, and train the system. So we get a new model, AM1. And then we take B1, add the second confidence bin, train a new model, AM2. And likewise, we do for all the bins we do. Now we have a test set to evaluate. T is a test set. We decode our models and get a representation, say, in terms of error rate. We will see it later, what is the WER. And then what happens generally is this AM seed model has some, say, X% WER. While training this with the new data, the performance improves and the word error rate drops. So this one round of iteration is it's not iterative, hence it is called non-iterative approach. But now, if we take the second model, suppose the second model was the best among the 10, we take the second model, redecode entire DU. This second model is better than the seed model, and hence this time the transcripts will be better and the confidence scores will be better. Again, we do the process of binning, retraining, building the caustic model altogether, and then we get new AM models. And again, we check for the error rates. If it is better than the previous one, we again take, say, AM5 this time is better. We take AM5 and start redecoding. We continuously do this process until our WER saturates. So this process is what is known as iterative approach of doing semi-supervised learning. This is the same thing, non-iterative versus iterative approach. In non-iterative, we just do one iteration, just one round of retraining. However, in iterative approach, we take as many iterations as possible until the word error rate saturates. So I'll be presenting my use case on Hindi language. I'm not sure how many of you know Hindi language, and the data is call center in nature. So call center is, yes, when you need to call, say, maybe the food delivery guy, say the cab guy, or something of the customer care. But that time, whatever conversion happens is basically the call center data. The call center data is difficult than your read data, your lecture data, etc. The nature of the data is what brings the complexity. First thing, it is conversational in nature, because it is a conversation between two people. At time, it may be three people as well. And being call center data, it may anyone can call to the customer care, and they might be native, they might be non-native, etc. The speech can be accented as well. And since it is call center's data, there'll be a lot of background noise. It can be babbled in the call center, because that is a scenario of call center, many people sitting at the other end, the agent side, sitting all together, receiving 100 calls. There can be a lot of babble data. There can be a lot of ringtones, music, etc. that comes up. Being the call center data, the call can continue from around 5 minutes to, say, 25 or 35 minutes per call. That is what we have at our end. And total data that we collected was around 1,000 hours of data for the process of building ASR. Because then call center application is such that once you get the ASR transcript, you can do NLP over it and do some analysis, say whether the call was successful call or not successful call, etc. Instead of manually listening each and every call and going to the feedback, you can just do some sort of NLP over it and try to get inferencing out of the ASR output. So we had around 1,000 hours of data. But the problem was that annotating it was a tough job. We could annotate around 100 hours of data. And even then, as I said, there was a lot of babble ringtones. For first go of training, we removed those noises and we were left with around 60 hours of data for doing semi-supervised learning and even training our model. We created 2 test sets for evaluation. Test 1 was just not having non-overlapping speakers, and test 2 had overlapping speakers. So this is on this data, we will do semi-supervised learning. We have 100 hours of clean data annotated, and we have 2 test sets. So as you can see here, we have some seed model, we have a test set to evaluate, and this unannotated data is what was the difference between 100 and 1000, around 900 hours of unannotated data is what we have. So a very initial problem that we faced was the data was having a variety of noise, and some files are very clean and some were extremely noisy. So if you do semi-supervised learning directly on noisy files, you may not get a good output. So what we thought is to divide the data into, say, increasing to decreasing level of noise that is there in the data. This information is not there with the calls. You just have a raw audio with it. You do not know whether it is clean, it is multi-speaker. We have no information at all. So we have to extract that information from the speech signal. One approach that I thought was using feature-based approach. In feature-based approach, what we do is we estimate the time varying signal to noise ratio for the entire call for all the files in the database. Then we estimate two features, F1 and F2, that is stated here. F1 is nothing but the standard deviation of the time varying SNR, and F2 is the difference of two means, M1 and M2. M1 is basically the SNR, mean of SNR is more than the average TSNR, and M2 is the mean of the SNR less than the average TSNR. These two features have been derived after a lot of visualizations of this F1 and F2 feature on the speech signal itself, and then we finally come up with two features, F1 and F2. What we see is if you plot the distribution of F1 and F2, we see that it just follows a pattern as shown in the figure. And then we went on listening those files which have high F1 values and high F2 values. What we found to a surprise was that F1 and F2 having high values were extremely clean, and those files having low F1 and F2 values were extremely noisy. So this helped us to bin and classify our entire data on base of clean and noisy pattern. We used the mean and standard deviation of the data distribution to divide it into 4 bins, A, B, C, D. So basically A is completely clean, B has some sort of noise, it can be any noise, C is mostly more noisy, and D is extremely noisy. So if you see on the top right corner, so out of the 900 hours of data that we had, around 170 hours classified as A, B had around 250 hours, C has around 400 hours. So on an average, the data was extremely noisy. So had we did semi-supervised learning directly on the data, we would not have that great results. So we first do semi-supervised learning on class A, extremely clean, get a new model, and then do semi-supervised learning on B and C and then D. As I also said, the calls are very long, ranging from 3 to 5 minutes to 35 minutes, but that is now how you can do ASR training. You need to split into various logical and sortable segments. So we just do a silence-based detection of the call. And if a silence is detected in the region of 1 to 3 seconds, we split the call. And if there is a lot of noise and there is no silence at all, we do some sort of thresholding on the amplitude, and then we split the data. Around 30 seconds of split is generally what is used for training the models. It actually depends on which approach you're taking, hybrid or end-to-end. So this is the main frameworks that we have used. As I said, there are two ways of doing an ASR. One is the hybrid ASR and one is the end-to-end ASR. Hybrid generally is you have a toolkit, state of the art, that was the Kaldi toolkit, and it has recipes for various speech application. Kaldi follows a hybrid pattern. It has separate. It has recipes for building ASRs for various databases. It builds a separate acoustic model, a language model, and it trains an ASR. ESPnet is similar to Kaldi in terms of processing the data, etc. However, what is there extra is the end-to-end architectures. Now ESPnet has evolved a lot, and it has many current research work that is there in terms of ASR, joint LID, etc. These are both the toolkits that have been used. So as I said, then we need to evaluate our data. So this is the evaluation metric that is there for ASR. Error rate, you say. So error rate is basically the definition. By definition, it means the number of substitutions, insertion, and deletion by the total number of words or units in the reference. Why did I mention units? Is because we can train ASR at a word level, at a character level. So hence the error rate is either word error rate or a character error rate, or if it is something between them, say byte, let's say this is how one of the recent training can be done. So we say it's a byte error rate or it's a token error rate or whatever it is. It's an example in English. If you see, the original audio said he tried to think how it could be done. But suppose A sir was wrong and it said he tried to think what can be eaten. So if you see, so what is the thing? The two words have got substituted. Say how has become something else, it has become something else. So it is a substitution error. Could was or deleted. So that is a deletion error. B is as is, and say done got substituting something else. This is a substitution error. This can be either the performance of ASR is bad, anything, or it can be either accent issue. Say the original audio was how to recognize speech, but maybe the accent was such that it became how to recognize speech. So if you just say both, just sounds very similar. So if you can see, there are two substitutions, and nice beach was never there, but so there are two insertions, and you just add both according to this, and what you get is the word error rate. So this is how evaluation is done for ASR system. That is error rate. It can be either word error rate or character error rate. We have been using NVIDIA resources as everyone does for doing this. V100s. This was a very old run, maybe 5 months ago. So these were on V100. But generally, you need a lot of GPUs to do ASR-based training. Okay, and so yes. So coming to the architecture. We have been using both, as I said, end-to-end and hybrid ASR. On the end-to-end part, we are using the transformer architecture. It is one of the recent architectures that has been proposed. Initially, it was for the NLP domain, but there has been many work that has shown now that speech transformers are state of the art. There are a lot of papers cited below that you can refer to. And as far as features are concerned, we take pitch features and log-mel filter banks to train the network. And since attention model has its own shortcomings, we again use the CTC for joint training and decoding. Basically, the idea is the model predicts a target sequence Y, and the input is the sequence X, which is a feature level representation. So this is how the training is done and decoding is done. We use multi-objective learning framework. As I said, we are using both attention and CTC. That is, during the training, both the sequence model and the CTC module predicts the frame Y posterior. And the weighted sum of both is what is used as the log likelihood scores. Now, as you can see, while decoding, we have used both sequence to sequence and the CTC. But since there's an end-to-end model, we have not used a language model. Language model, as I said, is generally used when there is a structure to the speech. In case of our data, which was conversational, you might not have a structure unless you're talking about a specific topic. You may just and have disfluencies, etc., etc. Language model helps, but the architecture itself, as it is end to end, it takes care. It learns from the audio itself, the language to some extent, and we will see this in the next coming slides. So this is a comparison that we have for hybrid model versus end-to-end models. So hybrid model, as I said, you build a separate acoustic model, a separate language model. The acoustic model in this case is a time-driven neural network. It was very famous for hybrid ASRs. And language model is, we have crawled the entire text that you could do for Hindi language, and we have built a 3-gram language model. On the other hand, for end-to-end technique, we use ESPNet, and we do character level training. We just do, since Hindi language is a monomapping, that is the sound and the letter have only one mapping. We use character based approach to do training. Here we use the transformer architecture. And these are the results that you can see below. So what happens is, if you see Kaldi based system, they gave a performance around 37% on test 1. Test 1, if you remember, had non-overlapping speakers. So the test set speakers were not in the training set speakers. And hence you see the performance is slightly more than if the speakers are present in the training data. So, on the other hand, ESPNet, that is a transformer-based approach, was say independent of whether the speaker is present or not present, and also the performance was better than the hybrid ASRs. So what we do now, we have to choose why did we do the comparison. First of all, we want to build a seed model. We want to do semi-supervised learning. Amongst that seed model also, which to choose. Should we go for a hybrid approach? Should we go for a end-to-end approach? Based on our data is what we had to evaluate, and this is the result that show that you should go with the end-to-end architecture for building a seed model. So since, as we said, we will do semi-supervised learning on it, and we will add data that is of high confidence score to the seed model. If you see this interesting plot that is there, there's just a scatter plot of confidence score and the CR. So we have already got the results on test one, for which we have the ground truth with us. So we can estimate the CR, that is the character error rate. Yes. What we saw that the files having low character error rate were ones having high confidence score. So if you actually pick up data having high confidence score, it means it is almost correct, the error rate is very less. Then hence adding high confidence score to your seed model will definitely going to improve the performance. So this is what it looks like when you take the seed model. If you remember, we have bin the data in terms of bin. We have say DU, which is split it into bins. And remember, we again have divided data into classes A, B, C, D. A is completely clean. So first we will do semi-supervised learning on the class A, which is completely clean, and it had around 20,000 utterances. So this is what happened. There were very less files that were of high confidence, just 200 files having around in B1, that is more than 0.9 score. B2, if you can see, had around 2000 files, and so on. Majority of the concentration was around B3 and B4. So the system performance is around 33%. If you see, if 33% is the error rate, and if you just map to say 1 to 0, the majority of the files are in the bins having around 0.75 confidence score. So this is with the existing seed model. Now we have to improve this gradually by doing semi-supervised learning. So this is the results of the entire process. So as I said, we will do first semi-supervised learning on bin A. These are the results. So as you have seen already, this is by the ASP.NET framework, that is the end-to-end architecture. So we have the seed model, and on the two test sets, it has around 19% CR and around 43% WER. As I said in the initial figure, we will do one iteration. We will take the seed model, add those 200 files having high confidence score, and then we retrain the system. Then in seed plus B2, we will add 200 files plus 2000 files, and then again return with the seed model. So we get some again some performance. We do on this for B3, B4, and B5, and so on. What you see as here, what happens is, initially there is some CR and WR. When you keep adding data, what has happened is the performance has dropped, both in terms of CR and WR. If you further add data from lower confidence bins, B4 is something around 0.6. What happens is the performance starts degrading. This is the pattern that it should have. The CR drops and then increases. Why it increases? Because the lower confidence bins have wrong transcripts. As you know that this arrangement, those in B1 confidence are almost accurate, and in B2, that is around 0.9, are less accurate. And as you go to B10 or B9, those are very incorrect transcriptions. The moment you start adding data from this pool, you add wrong content, wrong annotated data to your ASR, and hence the model performance spoils out. This is evident from here. Now we again take this model and then start redecoding again. And once we start redecoding, we have new bins, as we said. And if you see, initially we had 48 hours of data. Now it has become 100 hours of data. We take this data and do iteration 2. A same pattern is observed, that the WR and CR drops and then it increases. We try to do iteration 2 also, but what happens is there is no further improvement. So we do iteratively this process for this class A, which was clean, and we see that the performance has improved for this particular clean set of data. So we started with a data of 48 hours, and we ended up at 111 hours without adding any data as a human annotated data. And the same is that the CR improves and the word rate also improves. So if you see what happens at the back end is this. The blue curve is what we have already seen. There is distribution of data in the bins when you decode with the seed model. Now we know that this is the iteration 0 model, and it has better CR and WER. So if you see the distribution of that model, what happens is, now B1 has more files. That is, with the new model, there are more files having higher confidence. That is, the transcription is much more correct than it was before. Same happens with iteration, the next iteration. If you see, the number of files in B1 has risen to around 9,000, and then it decreases. So you have many files now. You initially started with some 200 files in having correct transcripts, and you end up having around 9,000 files having correct transcripts. This is done without adding any human data, other human annotated data. So this is a process of doing a semi-supervised learning on just a cleaner version. Summarizing everything, as we said that we had four classes: clean version, noisy version, and so on. So when we did semi-supervised learning on clean data, if you see, the WER and the CR drops down. This is the WER, the CR drops down. Now we had bin B, the same process we follow. The same process, what happens is CR and WR decreases. We add bin C. It is the noisy. This is a noisy set. We keep on adding the data that we had. What happens? The CR and WR decreases. Yes, but what happens also is that the decrease is not that steep as it was initially. Initially, it was the performance error, that is a system performance, was going down very fast. And then as data was added, even though we added around 900 hours of data, there was very less improvement in the system performance. Why? Because the system has stopped learning. It has enough taken enough data that it can be obtained by semi-supervised learning, and the data process, the learning process is saturated. That is what happens. So even if you continue further, you might not get that much variation. That is when you sort to something like active learning. What is active learning and semi-supervised learning is, if I have to just brief, if you see that this course, we saw that on adding this data, your performance was improving. Obviously, those in the lower region were not showing that much improvement when you add. So semi-supervised learning is when you add the higher confidence bin and you get improvement. But there is always a low confidence bin that is not being exposed, and the ASR performance is I mean, the ASR is not able to make use of that data. So what you can do is, you can, if you want to give for annotation, we should give these data for annotation, because these data has complementary information. Something that is high confidence is that the system has already learned and it is no more able to recognize it better. But the lower confidence is the complementary information that even you pass, the system is giving uh, low error rates, or say low confidence, higher rates or low confidence score. That means the system wants to, that is a new data that the system has to learn to improve the overall robustness of performance of the ASA system. This is the entire semi-supervised pipeline that I intended to talk about. And this is how we have achieved, we have consumed all 900 hours of data and just annotated initial 100 hours. We have an average 4% to 5% drop in the CR and the WR, and mine 4% to 5% drop is significant if it is a conversational speech. So this is the overall results that we have, and this Hindi model, whatever we have, is in a good shape, deployed, working at various places. This is the semi-supervised pipeline and the ASR part, that work that we have been doing. So summarizing, as we have seen that semi-supervised ways is a good way to use unannotated data. What it matters is how to use the seed model. If you build a seed model on read speech and try to decode something on the conversational side, it may not work. So having a good seed is a key to do semi-supervised learning. And the nature of your test scenario, how is it, like how in our case we had to do this binning process, that is divide the data into clean to noisy case. You might have to do such processing to extract significant content or significant improvement after semi-supervised learning. We have seen that after some time, semi-supervised learning saturates. That is, even if you keep on adding data, the system does not learn, because there is nothing new to learn. In that case, you may resort to something like active learning, give the lower confidence score to the annotators, and they can annotate the data, and you can add the annotated data to your model to improve the performance. Okay, so I think that was my part on the ASR part. Now, relating to speech pathology, where majority of your expertise lies, uh, yeah, ASR systems are there out, a lot of ASR systems, and but where do they struggle? I mean, even the system that we have built, it struggles at a lot of places. One of them that we saw it is accents. And even if you just test any of the open source models out there, if you try any of the variations, say you add any non-native speaker trying to speak English, or any such thing, what happens is that this ASA system just fails out. Why it fails is because ASA systems are what it is trained on. So if you give certain data to it, it learns that data, and anything beyond it is unseen, and it holds true for domain as well. If you build a ASR system for, say, news, and it may not work for your movie content, or you say a generalized ASR, so there's nothing. So there's a concept of a large vocabulary, but then just imagine a large vocabulary mean you have to deal with medical terms also, and it's really hard for ASR if it has not seen that data to predict medical terms, say the names of medicines, or say any other cases like that. So what happens is that ASR system becomes biased to the data that they have, and this removing the bias in the what you call data is a very current research topic that people are taking, because if ASR has to be used by all, it has to be not biased, it has to be diverse, and that is the way it should work. So if you consider that systems that are there existing, so there are many languages in this world. I'm not sure if you can count also with considering the dialects and accents. In India, at least there are, say, thousand languages with dialects if we have to count. But if I have to count for how many languages do we have in ASR system, I can say maybe 10, not more than 10. So it is a very small proportion for which ASR systems are actually available out there. And even if a system is available out there, whether it works for all kind is a question to ask. So especially in the case of voice pathology, I'm sure there'll be hardly any ASR available. That means people who are having voice pathology, have speech impairment, they cannot use this technology because there's a bias that exists with the ASR, and the ASR cannot perform well. So it is just calling it something like they are deprived of the digital voice based access that is there out there. So if you need to do something for everyone in general, we need to see how the ASR can be even made unbiased, and it can be open to at least it's just very difficult. It's a very open research area. I mean, building ASR that works for voice pathology, how will even collect the data? I mean, people are already struggling to talk, and on top of that, we want 1,000 hours of data to build an ASR. How is it even possible? So these are very hard problems. It can be thought of various angles. How do you collect data is a thing. If not generate data, I mean, what are the options available to do ASR in voice pathology is something that needs to be. I really like this topic of bringing in diversity in ASRs, and this has been starting by the paper I've mentioned below. You can all look at it, and it's the current area to explore. And in case of this particular forum that I've presented, I think ASR for voice pathology, for people with voice pathology, is an open research problem. So that's it. I would like to thank my team members at Cognate, Professor Ram at IIIT Bangalore, for all the technical guidance he has given to us for a semi-supervised learning approach. And there are our research team at Cognate for all the discussions that we have on their existing databases. This entire pipeline of semi-supervised language is not only applied to Hindi, it has been going on for English. When I say English, it is actually Indian English, because Indian English is accented English spoken by Indian people. And when it is Indian people, it is like having as many accent as much as the language. So it's English spoken by South Indian guy, English spoken by North Indian guy. All this, when we have to build an ASR, it's a really tough job. So we are at Cognate, we are working to have a model that is taking care of accent as well. But the solution that we are proposing is the data and using semi-supervised learning approach. There can be other approaches to do that. One is feature-based approach, or network-based approach, or something else that needs further investigation. So, okay, this was the talk.
Thank you.
I think I finished before time, very before time.
So we have a lot of time for questions. Please, any questions? Please speak up, because I can't see everyone. Yeah, Thomas.
I have one. Yeah, I have one. First, thank you for the presentation. And my question is about the results you got. All of them. Like you have this, well, let's take the seed model. So you have this test 1 and test 2, and one is overlapping. So test 2, if I'm not mistaken.
Yes, so
and test
test
one is not
non-overlapping.
Yeah,
Yes. Yes, so test.
and
So
my
in this
question,
test one, yeah. Just go ahead with the question. Yeah.
Yeah, my question is, how do you explain that you overlapping tests, like in an end-to-end, perform like better than the non-overlapping
Yeah.
one?
So what
And why is
happens
it
in test?
performing
Yeah.
so well?
Yeah. So what happens is in test one, the speakers, okay, when not the speakers that were there in test one when were not in the training data. Suppose your speech was used in training data, it was not in the test set. Okay, or say my speech was in the test set. On the other hand, test two, even your speech was there in the test two. That means you're training the while training, this model has already seen your voice, right? So that's why it said overlapping. So the speakers are overlapping, and since the model has already learned, the performance is going to be better. So that is the explanation of how the results getting better for overlapping case. That is, the data has been overlapped. It is same for any sentence. Suppose a sentence. So overlapping can be in. I have done speaker overlapping. It can be even text overlapping. So the same text but is spoken by different people. Text overlapping. If both are overlapping, it's going to be very good results. But that is not the case how you test a ASR system. You have to, I mean, keep it very different. Your testing scenario, training scenario should match, but not that it should have all the same classes, even the speaker, etc., etc.
Okay, so when you mean overlapping, you say the speaker are also in the
Speakers,
test.
the speakers are
Okay.
the same. Yes.
Okay, I thought it was like the two person were speaking at the same time because it's a conversation.
No.
Okay.
No.
That's why I was a bit confused about
Generally,
this
what
result.
happens in overlapping speech is, okay, you thought in that case, if it is overlapping, then the word array should go high because the system does not understand. If the people are, if here what you have taken care that even if there is an overlap, the main speaker is saying. So when you transcribe, suppose we both are talking and you are just adding fillers, say okay, that is your overlapping. But then when we annotate the main speaker, and the speaker having this in between fillers, he's annotated if he's saying after I mean not overlapping. He should, after I finish sentence and then you say then it is annotated, else it is kept as a background speaker or something.
Okay, thank you.
More questions? Yeah, Ray.
I would like to ask a follow-up question. As you said, because test 2 has overlapped speakers, then you can also see it from the results where you have those dashed line and the solid lines. And you see higher, I think you can see.
You want me to go to that slide?
Yeah.
Is it this slide you're talking about?
Yeah, correct. Thank you. So you see a higher character error rate in test 2, but lower character error rate in test 1, right? However,
saying
you
higher?
you
Yes.
have speaker overlaps in test 2.
So, I mean, if I get your question, you're saying test 2 has overlaps.
Yeah.
Okay. You're talking about this result? Yes, because okay.
The one below it, the dash one.
You're talking about CRs.
Yeah, well, I actually want to talk about both because you can see difference for the characters, well, the character error rate, but for being A, you see,
Yes.
well, the two solid lines are quite.
Yes, I get your point. So it depends on, see, what happens is when you choose the test set, right? What we do, we have chosen randomly the test set. Okay, if you want to remove all sort of bias that is there, actually, I get your point. What you're trying to say is test 1 should be what do you call above this line and test 2 should be below this line, right? That is what you're asking, that is what you're saying. But that is not the only factor that depends, because when you create test 1 and test 2, we have just randomly sampled the data. It might be that the case that more difficult files that are difficult to transcribe went in test 2. Okay, and that is showing up when semi-supervised learning, and initially it was not showing up, maybe it is showing up now. So although the overall process of here is to show that both are decreasing, that is happening. But specific to your question, it is because the test sets are not I mean, what is the content? The actual text spoken is different. Had we taken test 1 and test 2 text same, but the speakers were overlapping, non-overlapping, then maybe this would have been the reverse. But this is happening because even the data, I mean, the actual content, if you see the amount of hours, it is not the same, right? So if you see this has some different data, this is some different data, altogether different. What if the phonemes are hard to detect, or whatever the files I hear, it's something different, some other words are there, which the model has not seen. Anything can be around that, and that is one of the reason. If you want to normalize all of this, we can just take test 1, whatever files, they should be spoken by someone else, but it is very difficult to get a case like this until if it is, I mean, you're actually asking the speakers to record and collect data. This is just conversation data out of nowhere. People will speak anything, so it is very hard to maintain this thing. Also, what duration of hours is overlapping and non-overlapping? We say overlapping, fine. Then how much? Or say, suppose speaker 1 was overlapping, how much? But that is unknown. I mean, it's not unknown, it's variable. Okay. So suppose speaker 1 was in training, speaker 1 was there for 20 minutes, and in testing it is say 1 minute. Okay. And on the other hand, suppose speaker B had only 1 minute of data in training, but in the testing he has 1 hour. Not the case, but there is a lot of randomness that is there in the testers also, because the data is such, you cannot have uniformity. It is conversational speech. If you want uniformity, it should be done on read speech, where you have recorded, you have a predefined test to spoken, etc. Here it is very, I mean, it's difficult to keep that test set in mind. Why we took 2 test sets is because we wanted to make sure that the overall pattern is a decreasing pattern. It does not we should not be guided by just one result. And what if that one result accidentally, because we did a random sampling, was a very good test set? We wanted to avoid that case. That we took 2 test set. We could have taken if we had some other cost center data, we can have taken a 3rd test set. So it depends on the data that you have, and etc. etc. But what you're saying is difficult to do in this scenario, keeping in mind that you don't have this repetitions there in the data.
Thank you very much.
So, anyone else has a question?
I think there's one in the chat. Thank you for presentation. Okay, in the context of atypical speech, pathological speech, where the annotated data is very scarce, what would be the best approach, hybrid or end-to-end? In your case, you used TDN for acoustic model. What was the phone error accuracy of the model? Okay, is there a way to improve the performance? Yes. So I can just go back to my slides. The question is, I think there are 2-3 questions embedded inside the same questions. Yes, so the question asked is, if it is a typical speech, pathological speech, what is the best way to go? I would say it depends on what is the use case. Generally, for this much less data, I mean, it's just 50 hours or 60 hours of data, we have generally seen a hybrid approach performing better. But in our case, what happened is end-to-end perform better. Why? Because it is not structured. It is conversational. Had it been the reverse case, say had it been some storybook recordings like Libri speech, it would be reverse. That is, since you're using a language model in your acoustic model, it actually takes care of the grammar part very well, and hence Kaldi general the TDN based approach, I mean the Kaldi based approach generally gives a very good performance over end-to-end architectures for less data, because it has a language model in place. So if you are wondering which to choose, Kaldi or ESP.NET, it should also take into consideration what data you have. Is it going to be structured or non-structured? Because the language model plays a part. Training a language model end-to-end requires a lot of data. A lot means a lot of data. I mean, but on the other hand, Kaldi can take smaller data sets also. The language models are really good, and the hybrid model works very good for structured data. If it is that, this is what we have seen. But I have always got this information that if it is a conversational speech, all our models, be it Hindi, Indian English, whatever foreign language we have work, conversational speech catches for conversational speech, that is non-structured speech, generally end-to-end performs better. And that is what, if you have pathological speech, it depends. What are you trying to say? Generally, I'm sure with pathological speech, why would someone try to read a book? Obviously, they're using for their purpose, to solve something, to get access to something that they want. I don't know how much of read speech will they choose. So obviously, like pathological speech, maybe never can be used for news broadcast, right? And never for say lectures. So maybe it's always going to be something where people are going to say conversational type, maybe try to talk. It will not be structured. Yes, not be structured. Then maybe end to end is a good thing. But again, it depends on the data that is at hand. How much data does, obviously we can play with the architectures. There's a lot of architectures that are available out there, and you can definitely play with them. But my gut feel says that if it is non-structured, it should be end to end to go with.
Anyone else a question? Okay, I have a remark about your for pathological speech. One aspect of pathological speech that's very difficult is that no two patients are the same. So there is generally a whole spectrum of severity between fully normal, non-deviant speech to hardly comprehensible or intelligible speech, which makes it difficult to collect data because, yeah, it's data. Actually, every application should be tuned for a single speaker, which limits the amount of data that's available extremely. And one application, you said they won't read books. Obviously, that's not the aim. But one application that's discussed at our institute now is if you have people with a voice problem, they have no real voice, so their speech is hoarse or difficult to understand. What you would like to have is a speech-to-speech translation. You recognize this deviant speech. This can be any deviation, a deviant speech, and then utter it in a normal, highly intelligible voice. And that means generally for purpose of telephones, calling over the telephone, speaking to other people, and this kind of Zooming presentations for Zoom. Because yeah, you can lose your vocal track, your vocal folds, and still want to be a teacher or a presenter or a scientist. So, but all these require systems that work with extremely little data, have to be tuned to an individual speaker, more or less. What's possibilities?
Yeah, one approach. I mean, since that's a point. I'm not sure how much has been even researched on, and that's why it needs further research on this. As you said, correct. Yes, so we have to fine tune. Since we have less data, one approach is obviously we should fine tune. Take a very say big model that we have, and then start fine tuning your pathological speech on that particular small data. Suppose you have this is how we do accent fine tuning also. Suppose you have a model for English, but you want to fine tune for me and who is not an American speaker. You can take that small amount of data and fine tune my small 10 minutes of data on that. Obviously, again, fine tune is data dependent, but at least what happens in fine tuning is at the background you have seen lot of data, and then you're fine tuning on that small model on small data. So you're using existing information that is about English language, and then you're fine tuning to that particular speaker. It is all the more hard in case of pathological speech because sometimes it's just not spoken. I mean it's difficult to do that, but one approach is that, and then followed we can do, once the text whatever we have, we can obviously do a machine translation to get the text in the other language, and obviously TTS can speak back to get the language to at hand. That is how generally speech to speech will work. But yes, the data that problem that you're talking about is tuning to a particular speaker. Yes, it can be done. Yes, but how much is it what do you call, effective in pathological speech is we really do not know, as but the data isn't available at hand. So what we generally deal with pathological voices, I had been working for the problem of normal versus pathological speech, and I was just working with few samples of A and voice sings. On the other hand, ASR requires sentences, so it's very difficult to even collect that of data. So I've known this problem 10 years back. I did my master's on this topic of classification of normal and pathological speech. I was working just with samples of vowels for 10 patients, and from that inferring anything is very difficult. And ASR, it's the next, ASR on them is nearly next level, and it's a challenging task, very challenging.
Thank you. Yeah, that's nice. Maybe you should come back to you later on. However, is there someone else who wants to pose a question?
Okay, Jim first, you please.
Okay, yeah, thank you for your presentation. And actually, I have two questions. One is that you show us one, like the result comparison, that table. So I saw, because you mentioned you didn't use the language model for the end-to-end training, that you use transformer. So how do you get the word error rate? Because you have the character error rate in the bracket, but how do you get word error rate?
Yes. Okay. Yeah. So I can answer that. So what happens is you train on characters, right? So we put an extra character. Suppose a language like Hindi has 75 characters. Okay. You put a 76th character as a space. Okay. So you even train on space as a character. So what it will learn is, in the acoustic model, space is generally a small silence between words. So it tries to learn that silence also, and then with your characters, you also predict a space. So whenever there's a space predicted, okay, I can just show it. Maybe I can. Okay. So see, if you have to do a character base, then this is the characters in English. Suppose you do this, but what you do, you also train with space as a character. So you just put a new character, space. So what it learns in the acoustic is, whenever something you tell me, this is the word that is spoken in the audio, how it goes is TELL space M space E. So obviously you don't feel, but between tell and me, there is a small, very millisecond type of silence that is there. It is visible in the, it might be visible in the spectrogram. That is what the model learns. And when it predicts, it tries to predict the space itself. And hence you just have to find the space and everything. So whenever it predicts in this way only. Okay. So wherever you just find the space, just merge everything that is there between two spaces and you get a word. That is how it is.
Okay, I think
It's
yeah,
yes.
go ahead. Okay.
I mean, that is how you predict the space. The system learns characters and it outputs characters, but that then you join those between those characters between a word, between two spaces, and you get the word out of it.
Yeah, but I'm a little bit worried about the case of co-articulation. So like we like it, when we say like it, there's no space. The co-articulation.
Yes, so that is the, yes, it's just one case. You will, because for ASA you don't need one file, you need a lot of data having a lot of context. So tell me somewhere here is tell me together, somewhere it may be tell me. It'll just learn from the representation. That is what it is.
Okay.
And if I have, and this results are very good for word array. It does actually predict the word breaks very nicely. It's there.
Yeah.
Something like English, you don't go a character based approach, but because the sounds, you read is somewhere read, somewhere it is read, it's all different. The E is not same everywhere, so it's depend on the language. At least for the language Hindi, it's a one-to-one mapping.
Yeah, okay, thank you. And my second question is regarding the semi-supervised learning. So I learned from your talk that it still requires a large amount of data. So you have maybe a small amount of annotated data, but you still have a large amount of unannotated data. But in like pathological ASR case, there's some case that we only have this small amount of labeled data, do you think we could still use make use of this semi-supervised learning?
As I said, again, the data problem first needs to be solved in the pathological case. We need to get the data at hand. Otherwise, the task is difficult. I mean, it's really something that I've not worked on. It's a tough one. That is, I have heard that people are doing. That is one of the talks I've mentioned in the paper. Okay, so you can just go to that paper, and there are many talks by Odette she has given. One of them was on inclusive ASRs that I just seen where they talk about creating the data also. I mean, is it possible? We tried this when we had no data. I mean, now we have 1,000 hours of data. What we did was we created data out of TTS systems. We took a TTS, fed in the text. Text is easy to collect. We just gave the TTS text, and it started giving out voice samples. Then we took their voice samples, and then we got a lot of acoustic data, right? But then it never had the variability that actual humans have, right? So we didn't find much improvement. I mean, it was just saturating after just adding few speakers because it was all synthetic. But yes, now since TTS is it is very natural and intelligible, I don't know whether we can take that route further.
Okay, yeah, thank you. So you mentioned the inclusive ASR. Actually, that's very interesting as well. But from my understanding, I think that's the opposite from the pathological ASR, because it's the goal is to dismiss the bias. So it wants to build a system that could recognize the normal speech, but the pathological or other accent speech as well. But for pathological ASR, we target, for example, we use the transfer learning, we made the system specific to this pathological speech. But it's actually, I don't think that's dismiss the bias in the system. What do you think of the difference of this two? Yeah.
I am not an expert about the inclusive thing. I'm just reading, but I'm not sure if I'm the correct person to answer that, because it's I didn't know that the paper that I have read, it's about inclusive ASR, and I came to know that accidentally I'm doing the same thing. I'm trying to remove my accent bias. As I said, I was working on English, and I was trying to remove Indian accent bias. But I never thought of the word bias until I read that paper. We all know ASR does not. We say ASR does not perform well. That is the way we say. But the term bias just came on recently, and actually I'm trying to solve the same problem. When I read the paper, and now I'm starting to use the word bias wherever wherever I go, because that is the correct way. We are making us ASR system bias. Yes, but if you see among the list that is there, gender, age, style, etc., 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 removing gender is maybe easy, age is maybe easy, then maybe accent, and at the last you can think of pathological speech. It's a really tough one.
Okay, yeah, thank you.
Thank you. Zhao, did you have a question?
Yeah, thank you, Tamina. Your topic is very interesting. I'm a new guy in ASR. I'm curious, in your semi-supervised learning, what's the exact measurement of the confidence score? Is it the probability?
Yes, so whenever we decode the ASR files, right, it is based on some likelihood scores. So as I said, we use a multi-objective learning training. So when the characters are predicted, each character is predicted with some confidence, some log likelihood scores, and then you can just do the inverse log, and you can get the scores the probability you can get from 0 to 1, and it's easily available on any of the tools you use. ESPNet now in fact populates the scores upfront. Before it was not showing up. Now they do show. You can tune it if you want character normalized scores, you want frame normalized score, whatever you want. In our case, we have used frame normalized score. For each frame, you get a confidence. You can normalize and then give an average confidence. I mean, it is just there now in any of the approaches that you take. Kaldi, it is difficult to get that. There's a lot of processing that is there, but yes, end-to-end models using ASP.NET, those are now coming with the log files. You just have to extract them.
Okay, thank you.
Thank you. I think we should close this this interesting question session because the next session is coming up with the ESR presentations. Sao, who's going to do that? I don't have the program.
Yes, in this afternoon, we will have one ESR presentation. It will be given by Viviana. Hi, Viviana.
Hello, good afternoon.
Hi, could you please share your screen?
Yeah. It says that I cannot start, it said. Okay. It's okay?
Yes.
Yes, I see too.
Okay, I also need to share some. Okay. Well, good afternoon. My name is Viviana Mendoza, and today I would like to present the idea of the virtual articulation trainer. Sorry. Wait, I have. Dysarthria is a motor speech disorder due to neurological damage causing weakness, slowness, and incoordination in the muscles that are involved in speech production, and impaired articulation of speech sounds. It's then a hallmark in motor speech disorder, and it's present in each type of dysarthria and also apraxia of speech, and reduced articulatory displacements or articulatory inefficiency cause reduced acoustic contrast and consequently reduced speech intelligibility. Within all the dimensions that contribute to speech intelligibility, articulation has a major impact. This was the result of a research conducted by Marc Devot and colleagues with a multiple regression model analysis, and a more recent approach within the frame of TAPAS. Another study pointed out the effectiveness of an intensive and direct articulation therapy on speech intelligibility, which showed a significant improvement and increasement after 1 week of intensive articulation training. And then we can then conclude that improving articulatory skills is often a major goal of the treatment therapy. And what we propose is a software program for patients with motor speech disorder. The main target group is 10 patients with articulation deficit, often elderly, and sometimes with brain damage. The aim is to guide them through an intensive treatment program for improving articulation and consequently speech production, intelligibility, and speech comprehension. Why a virtual tool for articulation therapy? Well, for a good recovery, speech treatment demands a lot of practice and requires a lot of intensity, but sometimes patients can have other physical disabilities or geographical barriers or financial reasons to not go for a face-to-face traditional speech therapy, and current solutions are limited, costly, mainly designed for children or with really complex interfaces that are not intended for patients with brain damage or elderly patients. What we want to offer them is then an accessible speech treatment in the comfort of the home environment, where the patient has the control over the timing and the intensity of the therapy program, which is designed, or we want to design it with an attractive and patient-friendly user interface suitable for patients, elderly patients, or with the brain damage. And it will offer individualized and customized therapy and feedback without the supervision of an speech and language therapist. The development of this software program involved 3 core steps. The exercise protocol, we need to carefully, or was carefully designed based on the principles of motor learning, the algorithm behind for error detection, and the interface with which group it all. I would like to show just a small part of the product, just a demo, and it's to give you a broad idea of how this product should work. And it's a virtual therapist that will give instructions to the user and will model the production that patients have to repeat. And after they do this, immediately they will receive feedback on the result. I will not show everything, just a part of the instructions and the model of the speech production.
Plaats beide lippen op elkaar. Plaats de tongpunt net achter de ondertanden. Laat nu de lucht ontsnappen via de neus. Gebruik hierbij je stem. Mat, oma, kom.
Yeah, a pilot study was conducted with 15 participants. Most of them had a positive attitude toward the use of the virtual therapist, and they feel the program can help or be helpful for them to improve the articulatory skills and the communication process. And they found very easy to use. In our business model, the target customers are patients with articulation deficit. We offer a one-time license for the acquisition of the program, but also a free installation. And we have also considered other opportunities for growing, and they are language schools and students learning a second language, which often need also some help with the speech production and articulation. In our team is composed by 2 speech and language therapists, and I am the biomedical engineer with a speech and signal processing background. And we love all to speak, and we also we love to give the chance to improve communication skills to people who need it, and where they can feel free to speak and safe while they are learning. Thank you for your attention.
Very interesting. Thank you, Rihanna. Anyone has any questions? If there's no question, I have a question about your application. It looks like there's already an app or a website being developed.
Yeah, sorry, it's already, no, it will be a software for to install in the computer. And yes, we have like a first version already that was that we tried with the 15 participants. So yeah, it's a software for computers.
I'm curious because maybe there are some people also have mental health problems, have some problems in their speaking. Are you also considering to merge some emotional guidance in your software?
Emotional guidance, no, I think we are not considering, because it will mainly target patients with mild and moderate dysarthria, not even severe dysarthria, but yeah, and also patients who can't work mainly independently with a computer program. So it's not designed for all kind of patients, unfortunately, but it will target a big population of affected speech. But I don't think we will target emotions in the program. It's just direct articulation training. So the exercises are mainly designed, there are two kinds of exercise, articulatory drills and minimal pairs. And yeah, they demand a lot of practice and intensity and timing. Yeah. It will be like a supplement of the traditional face-to-face therapy. It does not intend neither to be only that, but a complement or a supplement of the traditional therapy.
Yeah, so I personally just feel that would be interesting if it is also possible to be helpful to for some autism, depression, these kind of diseases.
That would be interesting, and yeah, probably in the future we can extend it, because yeah, it's intended to be easy and quite quite friendly to use. So probably in the future we can extend it with some other exercises or other type of exercises that can help also another kind of patients.
Yeah.
Any other question?
You could also write your questions in the chat. That's also.
I have a small question. You wanted to use it as a one-time license cost, but generally it means you will have to do some kind of maintenance for the program, and one-time license costs are tricky because the money is once there, and the maintenance period can be quite long. Have you thought about that?
Yeah, Rob, that is interesting. Thank you for the question. But no, the program is not intended at all to be paid for patients. It was just because in the training event 5, the last presentation, I say the application will be free. And the remark was, yeah, but you need to think in the business model and this and that. But no, indeed, the program will be available for all the community, and yeah, it's not
yeah, but generally you would like to have some kind of subscription model, and the subscription could be not to the users but to, say, the SLPs, the speech and language pathologists or the treating physicians.
Yeah.
In Europe, it's all about the insurance, health insurance payments.
Yeah, mainly therapy. It's covered by the insurance of the patient. So yeah,
that would be the most logical way to do that in Europe, at least.
Yeah, we will see. Thank you.
Thank you.
Any other question?
I'm curious in the technical part. If I understand right, from the patient's speech, you should give them some therapy suggestions according to some speech models. Is this right?
Yeah, they will receive the instruction of how to place the tongue, the lips, the jaw, so all the articulators, and after and also the like the video showed also the model of the word they have to utter, and after that the short instruction and video, then they will need to produce or to repeat what they heard. And yeah, the system will recognize how good or bad the target, because it's mainly working in target sounds. For like if the patient, after the intelligibility test, if the patient has problems only with the, let's say, 3 sounds, S, P, R, and M, for example, then he needs to train those kind of target sounds, and the program should give him feedback on the results of the production for the target sound. So how good or it was, or how, like an articulation score.
Okay. So okay, so the input is only the speech.
Yeah.
Mm-hmm.
It is only the speech, not an image.
Okay, because some years ago, I remember there's also some research, they put many sensors inside the mouth, and then they reconstruct the speech models from the data of the sensors.
Yeah, there are systems with the sensors, with image, with the sound. So, but no, we want to keep it as simple as possible. And yeah, it's like to work with sensors is lab based, but not not for users. So we only recommend to use a good headset and microphone to avoid noise, because external or background noise can also give misclassification in the target sound. So if probably was okay, and the patient will receive a score of low score because of the background sound. So it's only recommended to use a good headset, and that's it.
Okay, thank you. Any more questions? If no, would like to end the ESR presentation. And then Bjorn, please.
Yeah, hi, Joe. Hi, everybody. So welcome to the end of the show. And first of all, I'd like to spread out a massive thank you, of course, to Katrin and Zhao for running the whole event, and then to all the speakers we had in these days, but in particular to all of you. And before we end this, I would be very interested to hear some of your feedback. Do you have any talks that you like the most? Any remaining suggestions? What you missed maybe? So maybe we can be of help in doing something, or like, please, if you would want to say something. Nothing in particular. So let's hope that it was all perfect. How did you like virtual Augsburg? Anybody?
I have a little announcement. There will be a form. The customary internet form will be up to give all the details of what you liked and didn't like of this this course.
Yeah, that's perfect. That's the more anonymous way. Yeah. Yeah, thank you, Rob. And yeah, if nothing else, I very much would like to thank you, the ESRs, and of course, all other ones from the chair that helped to make this happen. Thank you also for the great presentations, but most of all, I really, really hope to see you someone soon in Augsburg. Please very much be invited to contact us at any time if you want to visit, if you are in the area, if you just want to collaborate or whatever. Well, with that, thanks again, everybody. And yeah, stay tapas and have a great afternoon. Thanks a lot. Bye.
Bye.
Thank you for organizing.
Bye.
Bye.
Thank you for organizing it all. Yes.
Bye. Thank you.